Okay, so since Sabine started the recording, I think we can welcome everybody to today's SimTech Colloquium in a little bit a new format, but I think it's great to be able to have George from Texas here without any long distance flights. So a very climate-friendly presentation today, George, although difficult without seeing people. So most of you will probably know George already. He's currently professor at the Oden Institute for Computational Science and Engineering at UT Austin in Texas. His group is a very good fit to SimTech. It's called Parallel Algorithms for Data Analytics and Simulations. So we have both data and simulations as we do have. George did his PhD in computational science and engineering at Carnegie Mellon, then moved on to New York to the Courant Institute of Math Sciences, so got his kind of math input there. He held faculty positions at the University of Pennsylvania and at Georgia Tech, and he won 2 times the Gordon Bell Prize. So I don't mention all the list of other prizes, George, but I think this is interesting for everybody here because that means that George really knows how to compute big problems in a fast and highly parallel way on a big machine. So we will see a bit of that today in the presentation. I have known George for a long time, so we also spent some time in a group together at the Institute for Advanced Studies in Munich. I think it was from 2010 to 2013 where George was as a Hans Fischer Senior Fellow at this institute. And yeah, you already have connections to SimTech as well. So if somebody wonders whether you've already seen George, you might have because he was in Stuttgart as a Argyris visiting professor in 2019. So shortly before COVID stopped down these actions. So George, we are happy to have you here. I won't say anything about the content of the presentation because I think you can do that yourself much better than I can. So please go ahead.
Thank you, Miriam. Thank you for the nice introduction and inviting me. And with Miriam, we had a very long collaboration field of medical imaging as well. But today I'm gonna be talking on something different, on scientific machine learning models for additive manufacturing. This is joint work with Steve DeWitt from and Bala Subramanian and Radha Krishnan from Crete National Lab and Yigong Chin from a student in my group at UT. And this is under the auspices of a project funded by the Department of Energy in the United States, EOLUS, on mathematics for complex systems. So here is the idea is we're going to try to model essentially crystal formation. So this area is liquid. These are different crystals, and the colors indicate different orientations, crystallographic orientations. And this is a phase field partial differential equation ground truth model. And this is a neural network that is trying to reproduce the same dynamics. And this is the point-wise error, misclassification error, basically at every point, at every pixel. We go and we look what is the grain color of the pixel, and if the simulation and the PD agree, then we have the beige, and if they disagree, we have the dark, and this is the misclassification, pixel-wise misclassification error. So I'll tell you a little bit about the problem, the algorithms, and some open challenges. So we're interested in a specific part of additive class of additive manufacturing. This is for metals, and it's called laser power bed fusion. And the idea is that there is a powder here with some grain statistics. Right here you can see it, and there is a chamber. And the idea is that this powder at every step of the production, this powder is deposited on top of the part that we want to build. This is solidified, and then the laser comes, this already solidified, the laser will come and start first melt and then solidified and bring the layer, the next layer of the part. So this is the idea in manufacturing. Here we cannot see the laser, of course, but you can see the process. And then you can get, the idea is you can get very complicated geometries that are basically done in one pass without any welding and any other kind of connecting mechanisms. This is an example of a very large part. This is the Super Draco engine from SpaceX that has been additively manufactured. And these are some of the major companies that provide solutions in this space. And what are the engineering and mathematical challenges? From an engineering point of view, of course, we will have not only to control the shape of the final part. You can see here the complex structures here that are additively manufactured, but also we want to control the material properties, the strength, the porosity, and also accelerate the certification. It turns out there is quite a significant variability and the interplay between the powder distribution, the material, the laser parameters, the machine, how the path on how we decide to realize the shape, and that can create problems with respect to excessive porosity, cracking, and failures, and basically quality. And in order to have something that will go to aerospace or biomedical industry and has to have certain quality warranties, it could take up to a year or more to certify the quality of a part, and we would like to accelerate this process using numerical simulations. On top of that, because the process is inherently stochastic, the powder variations in the laser positions, the complex multiphysics, we will want to carry calculations related to uncertainty quantification, Bayesian inference, and even optimal control under uncertainty. And all these outer loop tasks, again, impose even higher computational costs, as we want to essentially be able to solve and simulate in many times. The challenges in this problem are multiphysics, non-stationary, non-equilibrium physics, moving interfaces, and also the idea of building, let's say, reduced order or some kind of approximate solutions to the PD that were easy to evaluate, so we can carry on these tasks, can be quite challenging, both computational, but also how we generate training data to build these systems. The holy grail, as I said, is to be able to go from the melt pool physics, in which here we have the solidification, and here we have heat transfer, and actually Navier-Stokes equations, we have free surfaces. In fact, we have radiative heat transfer, and very complicated physics, plus the solidification for the metal, in which will give us the final microstructure. Then, even after the process ends, because of the heating and residual heat, there will be some grain formation that will create a residual stress, and then we want to find some effective material properties using crystal plasticity, and then put these kind of inhomogeneous material properties into a part simulation, in which then we're going to simulate the performance of the part under the actual operative conditions. So it's a multi-scale, multi-physics problem, and this is a picture from this paper by Turner and company from Oak Ridge and Lawrence Livermore Laboratory, and there's a huge multi-million investment from the Department of Energy in the United States in building this exascale capabilities that you can go from integrate all this physics that you go from the melt pool all the way to the part performance. So that's kind of the holy grail, and this talk will just gonna focus on simplified models for these two parts, basically the heat transfer and the microstructure formation. And this is a little bit more specific problem statement, a simpler problem statement, in which what we're going to do, actually, we're going to see just the case in which we have a laser that shines in this position. It melts a semi-spherical region, and then this liquid metal solidifies. And you can see here there's a laser. There is this is the temperature. You can think the white region here is liquid metal. This is solid, and then we're going to turn the laser slowly off, and then will be the cooling and the microstructure formation. And this is the very simple setup. The heat equation can be, the melt pool physics can be very complicated, but here we're going to use just a nonlinear heat equation, which I'm going to discuss shortly in a subsequent slide. And then we're going to use kind of a phase field in order to capture the microstructure formation. So here you can see what's called dendrites, but essentially these are crystals, and every crystal grows in a specific orientation. This is the crystallographic orientation. And then the interface between crystals and the different orientations creates stresses, and then you have to go to crystal plasticity to take basically these statistics that will go down to a finite element crystal plasticity code, and then we'll do some kind of averaging to find effective material properties, yield surfaces, etc. So that's kind of the workflow. And our goal is to be able to approximate this phase field. We're going to assume we have an existing solver for the heat transfer problem, and we're going to get the temperature field, and we're going to drive basically the solidification. And our goal is to build, as I said, a quick, fast algorithm that can approximate this crystal formation. Also, I forgot to say that if you have any questions, please feel free to interrupt me at any point through the talk. Just don't use the chat because I'm not monitoring. Just speak up. I'll be happy to answer questions. This is a simulation that we did in the lab. This is before we show the simulation, just to explain what we're going to be seeing here. So this is half of the melt pool. Imagine there is kind of a symmetry. There is on the other half to the right will be the other half of the melt pool, but we use symmetry boundary conditions in this part. And here what you see, this is solid metal. These are alloys, so these are mixtures. So this is a nickel aluminum alloy, and there is composition variation, and this is kind of a metric of the composition, and that's important also in the properties for of the final material. And here you can see essentially these are crystals that grow, and these are what's called dendrites. They have this almost like snowflakes structure, and this is a liquid metal, and we're going to see how this process evolves. Just to show you the dynamics. So here we already have the heat profile. We have solved the heat transfer, and then we given the heat profile, the cooling essentially, because it slowly cools as we go in this direction. They solidifies, and you can see the solution of a partial differential equation phase field that captures this microstructure formation. And that's the simulation, and that's what we try to capture. Now you can see probably here the different orientations. So for example, you can see dendrites growing in this direction, and dendrites growing in this direction, and dendrites using in this direction. These are essentially different grains that are these directions are captured in this figure, and that's another simulation in which we can map this dendrite formation to the grains. So there are two problems here: capturing these alloy variations in the specific dendrite microstructure, and also the second problem, which is perhaps a little bit easier, is try to capture the grain distribution. So when we say microstructure prediction in these problems, what we mean is how big the grains are, what is the dominant orientation, how many grains are left, what is the size distribution. So microstructure prediction is basically statistics on the grains, the size, the crystallographic orientation, their size, but also it's a random variable because it really depends on the seeds. So here, these colors here that you see is basically some random substrate distribution. The metal in the substrate already has a grain, and here we just take it a uniform distribution with the size and the orientation, and that distribution affects, in combination with the heat transfer, affects what will be the final grain calculation. So in essence, in order to, when we do the solidification, since this is unknown, it's essentially a random, the solution or the quantities of interest are random variables that depend on this random distribution, the initial grains. And that implies that whenever we do a simulation, even for a single melt pool, we have to perform this simulation that you see here several times in order to basically sampling this distribution in order to obtain statistics for the microstructure, the texture here. Does this make sense? Any questions so far? What the problem statement is? Okay. So these are the simplified set of PDEs. So this is a heat transfer problem. The heat capacity and in fact actually the conductivity depend non-linear in the temperature. Here we ignore this dependence. The boundary conditions on the top of the surface where the laser is will be the laser source, some convective term and some radiative term. And then in the other parts of the boundary, we're going to have a zero flux, or assume it's large enough. And then given the temperature profile, then we solve this phi here will essentially capture it's going to be an indicator, a function that captures whether we have solid or liquid. And then we have this U function that essentially captures the concentration of the alloy. It's a nonlinear parabolic equation. This is a diffusion term. This is the time derivative. This is a nonlinear anisotropic that has the grain orientation. I'm not going to go into the details. You can see quite messy. There is a nonlinear advection term. There are kind of penalty terms from a phase field in order to have a 0 or a -1,1 penalization to indicate solid or liquid. And plus additional terms that have the temperature. It also has this C variable here, which is essentially a random variable. So this is in fact a stochastic partial differential equation, and this term is required in order to trigger dendrite formation. So the problem is very challenging, and also the initial conditions, as I said, they have the initial grain distribution. So it's a stochastic differential equation with random initial conditions. So this is the stochastic PD. The solver is an explicit forward Euler. Due to the stochasticity, we didn't go to higher order, and we use vanilla finite differences. The system actually, the time scales are such that an implicit time stepping doesn't really offer much, so you have to march explicitly in order to resolve the dendrite formation. We only do some nonlinear rescaling, which is standard in the literature, in order to accelerate the calculations, and we have what's called a translating observer frame, which I'm not discussing now. We have a GPU and GPU-aware MPI for shared and distributed memory. And also we have parallelized the quantities of interest, recovering the grains, recovering the microstructure, and doing the statistics. So in some sense, the solvers are quite standard, explicit finite differences, but we did some care in trying to optimize performance, and this code runs on multi-GPUs using MPI. So what is our goal? Our goal now is to create a reduced order model that runs much, much faster, that essentially takes as an input the size and the number of the initial conditions for the grains. What is the substrate, this substrate distribution right here. It takes the geometry, what is the melt pool size from the heat equation. It takes this what's called GNR, but essentially these are temperature derived. So this is the temperature field in some sense. And then the material, what kind of material we have, this is this parameter here. Or the power statistics. And then from that, we can sample, if we have the reduced model that basically given as an input these parameters, it returns the quantities of interest, which is, for example, the grain size distribution and the orientation, we can sample. Then if this is very fast, we can sample this input, and then we can produce statistics of our quantity of interest. But the goal is essentially to train the reduced order model. We're going to be using a neural network to predict the Q of I. But it's quite challenging because generating training data for the Q of I, if it's not properly done, it can be even more expensive than actually computing directly the Q of I doing phase fields. So we really took care of trying to minimize training costs in order to make this computationally feasible. So the main idea is to actually train on a small 8-grain domain. So when I say 8 grains, we have 8 grains in the substrate, which is really tiny, on a very simple rectangular domain, and then sample our inputs. So we will be sampling the grain distribution right here, the initial condition. For example, what is the orientation and what is the size of the grains right here. We're going to sample this, the heat transfer and the material properties, and then we're going to have different data sets in which we're going to use as ground truth to train a reduced model. But then once we're going to train, we're going to have kind of physics-based ways to extend this to actually larger number of grains and in fact actual melt pools. For these target configurations that correspond to the actual material, we're not going to train at all. We're going to be using this model. And so that's kind of one of our main contributions on how to really minimize the cost to train the data and of course the structure of the reduced order model. So let me now walk you through this idea. So the basic idea is again, create this training set and train the reduced model on these images. Now one can say, okay, these are kind of 2D images. Can we just train a standard image-based neural network that takes this image here and produces the different images at the end? So kind of UNet or encoder-decoder network. We tried that and that was a bad idea, it didn't really work very well. So instead what we do, we use the nature of the problem that essentially we have what's called epitaxial growth, in which the grains grow following the temperature gradient. And instead we have these manual features in which instead of representing the whole thing as an image, what we represent is the current height of the solid liquid interface. For every grain, we store the width of the grain at the top, at the solid liquid interface, and some excess area because the interface is not completely flat. So we're not going to resolve these complicated shapes here, but instead we're only going to resolve, we're going to represent the scalar variable that says how much extra area is on top of the average solid liquid interface. And these will be functions of time and will be for every grain. So this will be our manual features. So essentially the height, and for every grain, its width and excess area. And now once we have that, you can actually reconstruct. So imagine that if this is my initial condition, and these are these features at different time snapshots, we can have a reconstruction, let's say by linear interpolation, in which from these snapshots, we can go back to the original microstructure. So there's a way to go back and forth between these manually handcrafted features that compress the phase field representation and the actual phase field representation. So these are our manual features, and now our goal will be essentially to predict these features at every time step. So we're going to be training, we're going to be running a forward simulation, we're going to extract these features, and then we're going to try to predict them using the reduced order model. Now, the model that we use is a time evolution, sequence to sequence, long short-term memory deep neural network. Too many words here, but the idea is we want to capture somehow, as opposed to the PDE, that essentially when we discretize, the current time depends only on the previous time. When there is a reduction of unknowns, there's a dimensional reduction. One can prove using simple linear ODEs that the moment you reduce the degrees of freedom dramatically, immediately you introduce history terms. So in some sense, if we wanted to reduce this model, we will have to have a term that involves memory, basically all the history of the previous simulations. And that's what these LSTM networks do. Essentially, they don't really use only the previous time step, but they use the whole time history of the evolution in order to predict the next sequences. And then we have what's called a self-attention, which is the kind of transformer architecture that allows us to capture interaction between grains. I can, if we have time at the end, I can speak to it a little bit. In the 2-dimension, we have the main gain is in the reducing the time steps. So in some sense, for the PDE, we need thousands of unknowns for this 8-grain configuration, and the grain NN has about 10,000. I mean, it has actually 90,000 variables for the weights, but we only take 10 time steps as opposed to 1,000 time steps for the PD. And also the structure of the calculation here is compute bound as opposed to this one, which is memory bound, being a low order explicit. So we get both efficiencies because it's a more compute bound calculation and also fewer time steps. So I'll give more details on the network when we do the 3D extension. But that's how we proceed for the training. This is 2 values of material and isotropy. So we have 3 main parameters that capture the physics, and then we have the grains, the random variable for the grains. So that's our input. And here you can see the what's called the GNR, these 2 parameters. The gray values are the sampled values that we have. So this range of values here for the epsilon and G are related to a specific alloy and specific additive manufacturing conditions. And these are the range of materials. So the gray values indicate where we sample to create training samples. The blue values are where we did just one PD in order to check the error. And the star values is where we did multiple PD solvers in order to compute the statistics and compare the statistics. So between the predictions, the inference, and the ground truth. Generating these 24,000 phase field simulations on the 8-grain took about 36 hours on a single GPU, and then training the network took about 11 hours. So if you have multiple GPUs, of course, this it's embarrassing in parallel. You can make it as fast as you want to generate the data. And then training took, as I said, 11 hours on a 3 GPU system at Texas Advanced Computing Center. And then these are indicative results for the some of the blue dots in the testing. So these are again 8-grain testing values. So this is the prediction for the PDE, and this is the simulation that we come for the grain. So if you can see here, there is a little bit of curvature that we don't model. We just have the excess area, and you can see the errors here. We get about 3 to 5% error. We call this in distribution because we train for 8 grains and we test on 8 grains, but in different parameters. Now, what we're going to do here, we're going to use physics-based extensions, which I don't want to discuss, that allow us kind of domain decomposition to actually do 128 grains, in which we never really trained for. That will be extremely expensive to train. But with this extension, we can use the 8-grain neural network in order to predict this simulation. And you can see the errors can be, the point-wise errors actually can be quite significant, right? So for example, you can see here the structure in the phase field is somehow different from the neural network. But the overall, in the eyeball norm at least, the structure is the same, and here you can see the precise misclassification errors. Again, when you see dark, that means the pixel is classified to the wrong grain. And the PD solver took about 1 hour, whereas the grain and then the inference took just 3 seconds. But more interesting now, we can do melt pools, and that requires essentially taking an initial substrate distribution of the MEL pool. There is a coordinate transformation in which we unroll this and we make it flat. It's a mapping of this quarter of a circle to a square. And then we have some parameter transformations in order to create map the input here to the input to the rectangular domain. Then we apply grain NN, and then we rotate back with some scalings, and we get the PD solution. And you can see here the error is about 9%. So we never trained for this configuration. And that's the simulation I showed in the opening slide, in which we now use the neural network in order to predict the microstructure. And these are different samples for the same GNR. We sample different initial distributions of grains, and you can see the error hovers around 9 to 10%, the point-wise misclassification error. So just to show you the overall cost, the 8-grain training, as I said, takes 24,000 8-grain phase field simulations. It takes 36 hours to run on a single A100 GPU, and the inference for one for all 2400 takes 124 seconds once it's trained, and the average error is about 4%. In the validation test, in which we use basically to tune hyperparameters, we get about 6% error. We use only 100 simulations, 1.8 hours and 5 seconds for the neural network. In the testing, similar numbers. And now when we do what's called out of distribution, when we increase the time horizon, or we have different distribution of the initial substrate, the initial grain size, or we increase the number of grains, we get a significant speed up. So we tested in all cases 100 phase field simulations. Let's say for the 32 grains, it took 60 hours for all these simulations with 32 grains, 60 hours, whereas the reduced order, the LSTM, takes 44 seconds. And the average MR is about 8 seconds. 8%. But now I want to emphasize that predicting point-wise voxel is both very hard and not our goal, but also kind of meaningless, right? Because we don't really know the exact initial conditions. So there's no point of doing super accurate calculations. We want to be able to sample, and what we really care is what is the probability distribution. So if we do some calculations and we compute several times and then we do averages, so for example here what we look is the distribution of the grain size normalized to the average grain size. So this is the histogram or the distribution of the grain size, and you can see the dotted is the grain, the neural network, and the PD. So we can capture the distributions extremely accurate for out of distribution, double horizon, and in the initial grain size, actually the size, there is some discrepancy that may or may not be significant. And then we can also see average misorientation. So this is only inference. We don't compare with ground truth because the calculations are very expensive. And so then once we have the grain NN, we can look, let's say, what is the average orientation for different parameters and create these maps that can go then to the downstream tasks for residual stresses. So, and that really makes grain makes these calculations feasible. It will be, it will take days to do it using phase fields, and now we can do it basically in seconds. So in 2D, I described this reduced order molet for stochastic multi-component nonlinear PDEs. It has several features. It has the manual handcraft feature to reduce the dimension. Then we have a physics-aware LSTM in which we use it in order to train in 8 grains, and then we're using physics-based extensions to map it to large number of grains and the melt pool geometry, and present the results on predicting the quantity of interest. One problem that we have, unlike standard PDs, there is no theoretical guarantees. It's only 2D. We don't model nucleation. Nucleation is when we have a grain growing here and then another grain starts nucleating. And certain materials, in certain processes, this is an important phenomenon. In additive manufacturing, not so much because the time scales are so fast, but it's something that we're looking at. We didn't try to model the dendrite microstructure and the alloy composition, which is important, but we have ideas on how this can be done on top of that. So in the remaining time, let me actually show how this extends to a real, more realistic 3D geometry, which we're going to use the same ideas, but the structure of the network will be a little bit different. So in 3D, again, we have some substrate of grain distribution. Again, every grain, essentially, it's a crystal, and the color indicates different orientation, different growth direction. And as the crystals grow, some crystals disappear. For example, these small guys disappear, and then we have larger and larger grains until the solidification ends. And once the solidification ends, again, we want to find what are the statistics of this microstructure. Typically, the length scales here are, let's say, 50 microns by 50 microns, depending on the application. But in metal additive manufacturing, this is the range of the melt pool. Similar to 2D, we're going to have extract handcrafted features to represent solution. We're going to evolve these features using a reduced order model and neural network. We're going to reconstruct the phase field and the grain microstructure from these reduced features, and then we can compute quantities of interest. The input will be the thermal field that comes from the heat equation solver, the random distribution of the substrate grains, and the output will be the phase field for every grain as a function of essentially a function of space and time. So essentially, we're trying to reconstruct the whole state from this simulation, and then we can compute whatever quantities of interest we wish to compute. So this is the idea. What we're going to be using here is, again, we're going to be using an LSTM with transformer, but now we're going to use graph neural networks. Essentially, we're going to take this microstructure, and at different time snapshots, we're going to look at the cross-section. We're just going to take the top surface, similar to what we did in the 2D, and we're going to, from these images now, so we're going to extract from these volumetric calculations, we're going to extract an image at different times that essentially captures the grain shape at this cross-section, and we're going to convert this image to a graph in which, with vertices and edges, we're going to endow every edge and every node in the graph with features, and essentially now this will be the network. The network will propagate, given the graph and the vertices, it will propagate the features to the next time. And how we can construct the graph? Essentially, we're going to have this junction between grains, and the edges will be essentially indicate the connectivity between two junctions. Notice that here there's some curvature. We're gonna ignore this, and we're not gonna model it in the reduced model. To find the junctions, essentially we look at points in the phase field solution in which the neighbors have three different phase field values. This is a junction between grains, and this becomes a junction in the phase field, becomes a node in the graph. So these are the black lines that essentially correspond to grain boundaries, but also that's not full. We're going to also have a vertex corresponding to every grain, and there will be edges between these the grains and the junctions, which don't show up in this grain. So the graph is a little bit more complicated than this picture, but you can think it as a simpler case. as a representation of the grain boundaries in the junction with some additional information. So that's the reduction, and of course it's a significant reduction because we don't have to store an image, but now we just store the vertices, positions, and the connectivity of the graph. Any questions on this? Reduced representation? Okay. Once we have this representation, the idea is to essentially predict the motion of these junctions as the grains solidify or merge or grow. These vertices are going to be moving. So essentially, we will have a regression problem, try to predict the position of these vertices. However, the big challenge is there is topological changes. Not only the vertices of this graph move, but we also have merge events. So for example, this grain here does not show up anymore in this graph. And this grain here is reducing and is going to actually, then after a few time steps, it's going to disappear. That means that certain nodes and edges disappear from the graph. And so we have to capture this kind of discontinuous topological changes. And that's the very challenging part that kind of we resolved approximately. But this is, I'm not going to discuss the solution because it's very, the details of the solution is complicated, but I'll give you I think the main idea. So this is a representation of the event. So imagine that there's one grain here, another grain here, another grain here, another grain here, and that's the interface or the phase between two grains. So what happens as the simulation goes, this phase will disappear. So in the next step, the phase disappears, and in fact, a new phase appears between the different grains. So notice that grain Q3 and Q4 are neighbors because they share a common phase, and Q1 and Q2 are not neighbors in the beginning of the simulation. But at the end now, Q1 and Q2 are neighbors, and Q3 and Q4 are not. That's an example of a topological change that we have to capture. We call this the grain neighbor event switching, because we have switching neighborhoods from Q3 to Q4 to Q1 and Q2. So this is neighbor switch event, but also we have the grain elimination event in which this grain here completely disappears, and then we have to change the structure. You can imagine that these topological changes are quite challenging. So in order to capture them, you have two networks. We use two networks simultaneously. One network, its job is to predict the motion of these vertices, and the other network is to give us a probability for edges and grains of these guys disappearing. So it's a classifier. So we use both a regression and a classifier simultaneously in order to, and then to predict the evolution of the microstructure. And the features for junction or for points are basically the position, the height, the temperature at this position, and the change with respect to the previous time step. So we also maintain the changes. And we want to predict essentially, this is the input, and then we want to predict the next change. And these are the grain vertex features, in which again we have kind of the center of mass of the grain, the orientation of the grain, the excess area, and the total the change in the area and how much it will move how much it moved vertically. And then for the edges, essentially we have the length of the edge and the features of the two nodes. So we have an encoder-decoder type of LSTM, graph transformer LSTM, in which we have the regression for the coordinates and then the probability for vertex merges. And once we have the classifier, then we kind of reconstruct the graph, which I'm not going to discuss now. But the idea is we have the features for edges and vertices. We get the graph at t-1 and its features at t-1. We solve a regression and a classifier. We get the classification probabilities and the new features. Then we reconstruct the graph at times t using this information. And then once we have the graph, we can go and reconstruct the phase field using the graphs at two-time snapshots. And the main idea is in the time stepping is 1,000 times coarser than the actual PDE. So I'm running out of time, but just want to show you some represented results in which we run. The training is about 1,500 3D phase field simulations. Again, the same idea. We're going to have a small number of grains, and we're going to extend it to arbitrary number of grains. So we train with about, I think, 20 or 20 to 50 grains because it's a random variable. This is a simulation in which we show how many grains disappeared, about 6,000. The actual value is about 6,500, and we predicted 6,000 elimination events. These are the quantity of interest, the statistics of the grain orientation between phase field simulations and grain NN, and for different temperature regimes, melt pool size regimes, and that's the phase field, and that's the graph grain NN distribution. And you can see these are different heat melt pool sizes essentially. You can see that the distribution, the graphs look different depending on the condition. And this is the reduced order model, and this is the phase field calculation. You can see the errors again can be quite significant. There is curvature here, which is not captured at all in our case. The grains have different shape. So the point-wise errors can be up to 20%. However, if we look, let's say, as we go in the height, as the process continues, the percentage of grain elimination events are very similar between the two simulations. The red curve is the reduced order model, the blue curve is the phase field, and the shaded areas is the variation across different runs. And you can see we can capture the elimination events quite accurately in the different regimes, and also the size distribution, this quantity of interest between the two. And these are more examples in which we also vary the grain orientation, in which we show the effects and the variability of the quantities of interest. Here we show a little bit in the first table the effect of the architecture. So this is a transformer convolutional network without memory. This is an LSTM with graph convolutional, no transformer, and this is the graph LSTM transformer convolutional network, and we show the results. And this is the training size. Essentially, we use pairs of graph at GT-1 and GT, and this is our training set. So we have 5,000 pairs, 10,000, 20,000, and 30,000 pairs. And you can see the errors and the effect. For example, if you don't have memory, the error can be quite significant. The transformers improve a little bit from 23% to 18%. This is the error in the positions, in the excess area, and in the classification error. And this is the misclassification in which we didn't compute for these guys. So that's the effect of the training size and the architecture. And these are the kind of give you an idea of the costs. The phase field simulation requires about 500 million unknowns and about 20,000 time steps. And it takes, for example, for this regime, it takes almost, a little bit less than half an hour, whereas grain NN takes just 3 seconds. And this is when we scale it to the domain without retraining. This is larger domains, larger number of grains. It kind of scales linearly in the inference. So the savings will be tremendous, because in a real scenario, when we build a complicated step, this is for only one melt pool calculation. So for every melt pool, we have to do about, let's say, 100 random simulations in order to predict the quantities of interest in this melt pool, and then we have to do it for every location of the grain. So actually training, this is a case scenario in which it really pays off the reduced order model, because we're going to train for a variety of temperature conditions in one spot, and then we're going to be able to run the grain neural network for the whole build part. So to our knowledge, it's the first time that this technology enables full part microstructure prediction using this neural network. So summary, we have now a graph neural network for 3D. The ideas we use in 2D kind of extended to 3D, but you're introducing the graphs. It's extremely efficient, including the cost to generate the training data. As I said, a part requires thousands of melt pool simulations, or if we have 100 samples per melt pool, we're talking about 100,000 phase fields that will take basically months to do the calculation, whereas we can do it in days, essentially, with the graph neural network. There are some limitations. Our GNR are kind of homogeneous right now. We vary the parameters, but we treat it as a scalar. In reality, they are inhomogeneous. There are no really accuracy guarantees. The geometry is simple here. We haven't mapped it to more complex melt pools in 3D yet. And as I said, non-nucleation. These are all things that we're working on to extend. And these are two papers that this first paper discusses the physics of the problem and the full melt pool simulations. Actually, I want to say that even phase field, nobody has done really full melt pool, and we're kind of the first to do a simulation of the melt pool that I showed you in the beginning. And this is discussed the 2D neural network, and the 3D now is under submission. Thank you very much for your attention.
Yeah. Thank you, George, for the presentation. Are there any questions? Just speak up. Otherwise, I can maybe start with the first question. If you're talking about a simulation with thousands or hundreds of melt pools, how are they connected? Are they connected physically in the simulations? And how do you then make this connection in the inference of the networks?
Excellent question, Miriam. So the way they're connected is by the grain microstructure. So what happens, let me see. Actually, that picture is here, actually this. So this grain microstructure here, we kind of take it randomly, right? The statistics are given. But in reality, you can imagine one layer, it will create, when you do a layer, it will create this microstructure. The powder will go on top of that and will start melting. So the way they're coupled is actually, one main way is by the statistics of the grain microstructure affect the next melt pool and on top of the layer. So in some sense, you have to do them sequentially, and the only thing that will change is that this substrate is not random, but comes from previous simulations.
Okay, it's kind of in the generation of these seeds for the grains.
Correct.
That is a kind of a fully coupled process, and then the simulations and the neural networks.
Yeah, I mean, the physics are two-way coupled in reality, but most people ignore this.
Okay.
Because there is this temperature here is completely decoupled from the phase field, but in reality, there's a latent heat term in this term that if we do it properly, it will be coupled, there will be a phi term here. And then the simulation is much more complicated because they are two-way coupled. But this is not done even in the high fidelity simulations. This term is ignored. The most important coupling is, as I said, through this, the grains of the previous melt pool affect the grains of the next one.
Okay. Yeah, thanks. Are there any other questions? Dirk, you switched on your camera just to be seen or also to be heard?
No, to ask a question. Thanks for the nice presentation. In the first part, you indicated that you included physics knowledge. I guess this is when you pad the snapshots that you predict, so via the boundary conditions, or how do you include physics?
Yeah, so the physics was scaling in the network layers. So when we do this parameterization in which the boundary, there is a coordinate transformation and the scaling, this is done actually manually, handcrafted in the network. So there are scale. Okay. The simplest thing to consider is that there is a layer on top of the prediction that scales the hidden layer or the neurons based on this coordinate. So it's not any super deep conservation law. It's just scaling parameters that account for the domain parameterization. There's also some overlap in the domain decomposition that we introduce consistency, but that's it. Essentially, it's kind of handcrafted, right? It's a handcrafted superposition of the network that is not left to be automatically, but it's done manually. Does
Thanks
this
a lot
answer
for the
the question?
explanation.
Yeah.
Yes, perfectly.
So if no one has another question, I would have one, a very high level and maybe stupid question. You're trying to learn this microstructure on the grain level. If you're only interested in statistics, why not learn statistics directly? Or is that only half the truth? And I mean, the continuation of the question would be how
So
is
that,
the...
yeah, so that's an excellent question. So the first thing is we try to do I don't have the results here. We try to do a kind of SVN or a random forest in which you learn directly the statistics. We found it difficult to generalize, but maybe there's a network that does very well. But the main reason we decided to go for this is eventually we want to be able to check residuals and check when this fails.
Yeah, you want to be...
Once I haven't discussed it, but the big thing is how do you check? Okay, you cannot check the accuracy, but can you check that the simulation is completely off?
Yeah.
If you
I mean,
have
you
the
want to...
surrogate and you go for the quantities of interest, I don't see any way to do it. But here now that we have essentially the time history of the domain, the simplest thing to do is to put it back in the PD and check the residual.
Yeah, it's more interpretable kind of.
Right. So you
Yeah.
can see exactly where, and also you can compute any quantities of interest that you want because this kind of change. But I would say the main reason we did that is to be able to check how this thing fails, since we cannot prove it's going to be correct.
Yeah.
At least we want to be able to correct the failure.
And is it true that in the end you're interested in the material properties at some point?
Yeah, at the end, the microstructure goes to, as I said, to crystal plasticity, essentially get the statistics, and then they initiate random grains that do multiple calculations to find the yield surfaces. This is and at the end you want the material properties, right? You want to say that this is the yield strength of the material, that and then you put it in a finite element abacus or whatever to do whatever the load of the material, try to predict failure and crack initiation.
But does that then only depend on the statistics or really on the microstructure?
I think in the statistics you can never know the microstructure exactly. But also now it's not only the grain statistics, but also to the alloy composition, which we don't model here.
Yeah.
There's also another thing which is called porosity, which again is not captured here. So there are several other physics we do not. The main thing is the alloy composition variations and the porosity.
Yeah, sure. Thanks.
These are all excellent questions. Thank you, Miriam.
Any other questions? Doesn't seem to be the case, but George, maybe we should talk about macro coupling. I'll send you something.
Sure, I would be happy to, I would love to start working on something different than brain tumors.
Yes.
And this is the macro is very interesting, I think. But again, thank you so much for inviting me. It's kind of, I wish I was there to have the chance to talk to all of you individually, but hopefully in the future.
Would also be good to have dinner.
Yes.
Although it's breakfast for you.
Nice run in the beautiful Stuttgart. All right.
So thanks, George.
Thank you. Thank you so much.
Have a good day and see you soon.
Bye-bye. Have a great evening.
Bye.